So, continuing our discussion of bivariate and data analysis, we're going to talk about linear regression. So we've talked about building a relationship between variables. We can now fit a line around the scatter points, and we can quantify the relationship and explain the impact the explanatory variable has on the response variable, and use it for some limited prediction. So, when we're talking about a line can be described as y equals b plus mx, where y is the y-axis value, m is the slope, x is the x-axis value, and b is the y-intercept value. Now we describe a linear fit for a regression line as y is equal to alpha plus beta x, where alpha is the y-intercept parameter and beta is the slope parameter. For a sample, we fit it as y is equal to a plus bx. Now remember that the y-intercept is the value of y when x is equal to 0. This is your base amount of y. And slope is the rate of change in a line. So that is to say the amount y changes for each 1 unit change in x. Now, let's talk about how we fit a line. We can see here, this is real data, the relationship between divorces and gross domestic product. And we can see here that as gross domestic product rises, we tend to see an increase in divorces in Canada. So, but how do we fit it? Because we can see here are 4 lines fitted to the scatter plot. And it's difficult to say. We don't have the tools right now to say which of these lines fits best. But that's where linear regression comes in. We use what's called the least squares regression methods. Least squares refers to the fact that it minimizes the sum of the squared residuals. Residuals are an error term, and they give the difference between the fitted value of y and the actual value of y for a given x, and they're usually denoted as epsilon or e. Now, this methodology is used because it corresponds to the maximum likelihood criterion of the experimental errors of a normal distribution, and it can be derived as a method of moments estimator. This is basically a lot of words to say it's very elegant mathematics. So, all that's really important for purposes of this class that we use the least squares regression method. So, basically, we can estimate B as R, the correlation coefficient times the standard deviation of y divided by the standard deviation in x. And this is equivalent to the covariance of x and y divided by the sum, the square of the standard deviation of y, or the variance of x. And a is equal to y bar, the mean of y, minus the slope times the mean of x. And here are some alternate formulae you can use too that are very similar in nature to the alternate formula used for the calculation of the correlation coefficient. Note that b will always be in units of y per unit of x, and a will always be in units of y. So let's talk about our previous example to do some calculations. So first, we want to calculate the slope term b. And we know this is r times the standard deviation of y divided by the standard deviation in x. Now, we know from our previous work that the correlation coefficient r is negative 0.99. And we can use this table to derive that the standard deviation of y is the sum of y minus y bar squared, 0.692, divided by n minus 1, 4, and you take the square root. And we divide that by the sum of x minus x bar squared, divided by 4 once again because they have the same n. So 100,448,000 divided by 4. So now that's the same as minus 0.99 times 0.416 divided by 5,012.19, and now that leaves us with a slope of minus 0.00000 So this means that for each increase in X, each dollar increase in the salary, we can expect to see a 0.00082 decrease in mortality, or more efficiently, for every $1,000 increase, we'll see a 0.82 decrease in the infant mortality rate. So we can also show this works with the other formula, the covariance divided by the square, the variance of X, or the square root of the standard deviation. And we know from previous calculations that this is negative 2,064. You divide it by 5,000. 12.19 squared, which we get from our calculation over here. And you plug this into your calculator and you find you'll get the same 0.00082. So these formulae are equivalent. Now for the intercept term A, we know that's y bar minus b times x bar, mean of x and mean of y respectively. So y bar is just sum of y divided by n, so we have 14.8 divided by 5 minus 0.00082. Note that we have a minus, so this will end up being a positive. And x in this case is sum of x divided by n, 274,100 divided by 5, which leaves us with 2.96 plus 4.5 approximately. So our A value is 7.46. So our overall equation is y, our estimate. Y hat is generally how we depict the estimate. 7.46 minus 0.00082x. So that's how we can calculate the regression line formula, least squares. So just once again, for robustness, we can calculate the other method. B is equal to n sum of xy minus sum of x sum of y. You'll note this is the exact same numerator as the alternate method for calculating the correlation coefficient, and we might sit by sum of x squared and divided by sum of x all squared. And you'll notice this is one of the terms underneath the square root when we do that calculation too. So you can actually go look at your data there and pull these numbers right out. We see minus 41280 divided by 502240000, and we get the same minus the exact same answer. So the methods are equivalent. I generally find it practical to use the same method of calculating the slope coefficient as you use to calculate R, because as you can see the work, the correlation coefficient R, because the work repeats itself. I'm not going to do the alternate method because I find it to be very painful, and y bar minus b times x bar is the simplest method regardless of which method you use to calculate b. So you're welcome to use the alternate method of calculating the y-intercept, but I wouldn't recommend it. So with predicted values, once we have a regression equation, we can predict values for y for any value of x, even if we don't have an observed value. And all we have to do is plug it into the formula. But we have to note that we can only make predictions using values of x within the minimum and maximum observed x in the sample. You don't want to predict outside of the range you've seen because the relationship might not hold. Now, the perfect example I always like to use is the height of children. Because if you consider the height of a child, we can draw probably a pretty clear correlation between their age between 0 and 18 of their height. But you can't expand beyond that, right? You can't say, well, it grew, 3 feet between 15 and 18, so they'll probably grow 3 more feet between 18 and 21, and 3 more feet between 21 and 24, and they'll probably be 8 feet tall by the time they turn 30. It doesn't work that way, right? So obviously we know that, so that's the only time it'll be valid. So let's talk about practice. So assume we found a regression line between the number of dates and length of time in minutes a person spends discussing their self-insert Stargate SG-1 Gilmore Girls fan fiction. And we've discovered this. So from a sample where the minutes of discussion ranged from 2 to 20. So we want to explain the equation. So we know y is equal to a plus bx. So we could say that a, the intercept, is equal to 10. And we know this is always in units of y. And we could say that our relationship says that x is the explanatory variable, the spent talking about fan fiction, and dates is the response variable, y. So we can say we have 10 dates. And now because it's the y-intercept, we say we have 10 dates when fan fiction talk equals 0 minutes. So that's a satisfactory explanation. We'll expect 10 dates when you have 0 minutes of talk. Now B is slope. Sorry, I'm going to sloppy writing. And that's minus 0.4. And we know it's in terms of y per unit x. So we're talking dates per minute. So that means for each increase in a minute of talking about fan fiction, we see a 0.4 decrease in dates. So there we've explained it. Now, how many dates could someone expect after talking about fan fiction for 15 minutes? Is this valid? So we know y is equal to 10 minus 0.4 times x. And in this case, our x is, well, y hat, because we're estimating, times 15. 0.4 times 15 is 6. 10 minus 6 is 4. 4 dates. Now, is this valid? So we're estimating for 15. 15 is within 2 and 20. It's within the range of observed values, so we could say it is valid. Now, what's very important to know is that correlation is not causation. Correlation only shows a perceived relationship, that these two things coincide. There are numerous cases where other confounders get in the way and are actually causing the correlation effects. For example, a lot of effects, the perfect examples, the example we've been using throughout for correlation and regression, professor salaries and infant mortality rates. I'd love to tell you that they're related, and that means I should be paid more money, but they're not. The fact is both of these things have improved over time through inflation rates and better negotiation and more students attending school and higher requirements of faculty. Salaries increase. Salaries tend to increase in almost every industry over time. And they've increased in professors. And over that same period, we've seen better information in motherhood health, in medical technology, and so infant mortality has decreased. They're not, even though their correlation is quite tight, very, very high, they're not. It's not a causal relationship. This is probably the biggest mistake you see made in statistics, and one I hope I don't see out of any of you. If you have any questions about this section, correlation or linear regression, please do not hesitate to ask them on the forums or in chat.